Okay. Hey everyone, I'm Josh Schoolcraft, and the other partner in this little conspiracy is Thomas Werne, who isn't here. This is largely an overview of the software process for JPL's Inspire CubeSat mission. This mission is JPL's first cradle-to-grave in-house CubeSat mission. I'm going to start with an almost cliche quote. If you want to make an apple pie from scratch, you must first create the universe. That was kind of our mantra when we started this project. This is the first and last valid Doxygen tag you'll see. So there's going to be a little intro, which we're in right now. There's going to be an overview of Inspire, because I'm sure not everybody is familiar with this. We'll talk hardware and software architectures, and we'll talk development process, and a little overview of the code itself, and some reflections on everything. So I am in my 10th year at JPL. I like big hats. I worked traditionally in communications, so this project itself was a rather large left turn in my career. Thomas Werne, has always been working in instruments and flight software and ground support. For him, it was a little closer to what he'd been working on. He has some extensive CubeSat experience, while I did not before this time. So if this had been an Inspire mission presentation, the title slide would be this. I kept it in because it's got a nice call out of the backronym for Inspire: Interplanetary Nanospacecraft Pathfinder in a Relevant Environment. That's fantastic. So it's two spacecraft. The redundancy is in the fact that the two spacecraft are identical, and they are headed anywhere but Earth orbit, out of Earth orbit, deep space, interplanetary. We had a lot of collaborators bringing hardware for us to integrate into the spacecraft, so you can see a lot of partners here. So the spacecraft itself is a 3U CubeSat, 10 by 10 by 30 centimeters. A primary radio is an in-house built Iris X-band radio. It also has a UHF radio integrated with the command and data handling board, which comes from University of Michigan AstroDev. There is a coal gas ACS thrusting system for pointing mostly, an in-house magnetometer, a star tracker, and a payload processing board that includes a camera. Inspire was conceived as a small project, $5.5 million, with a small focused team. The core is 9 people. The largest individual sub-team would be software with 2 people. So I am half of the software team. The other half is observing from a secure, undisclosed location. The development cycle was extremely fast. We went from nothing to deep space spacecraft in 18 months, and we delivered on time and under budget. Unfortunately, we're sitting on a shelf waiting for a ride. We've got our thumb out, but there's probably some good news coming soon. The project itself was built on extensive CubeSat experience. A lot of the people on the project, except for me, have a lot of CubeSat experience from educational experiences and from JPL collaborations. The software team was multidisciplinary. Actually, the entire Inspire team is multidisciplinary. For example, at one point, I built a thermal chamber for the radio. It was an interesting experience. We focused on using existing standards as much as possible, and the mission, because it was a technology demo, is a technology demo primarily. We have a large margin for mission success. The requirements are simply survive, navigate, and communicate. Anything else is extra credit. So there is no science there. That is intentional. We expect to be able to turn on a magnetometer and measure the solar wind. The major constraints are definitely time. The depth of the team was a large constraint. And the hardware itself presents a pretty interesting challenge. So the command and data handling board has a primary processor from the Texas Instruments microcontroller family, MSP430. The features of this family are extremely low power with an idle current or less than a microamp. It's a von Neumann architecture. It has in-chip debugging capability, so you can single-step instructions and monitor the entire state of the processor as you step through a program. It is not radiation hardened. No member of the family is, although Texas Instruments is currently characterizing one of their MSP430 chips for rad-hard environments. You typically find these processors in things like smart faucets, remote controls, disposable electric razors. I didn't even know those existed. And the exact processor we are going to fly is actually in the Series 2 Fluke multimeter. And that is by far the most complicated piece of equipment I could find that is commercially available that involves these processors. The running joke with the team was that this sort of processor has the capability to run a microwave or a toaster, so we are teaching toasters to fly. Our initial design had a MSP430 F1611. It has flight heritage because it is a common component, especially in the AstroDev Cortex board, the command and data handling board. That chip runs at 8 megahertz, has 10 whole kilobytes of SRAM, and 64 kilobytes of on-chip program storage. However, due to a number of small problems we had with it, we went with a 2618, which has largely similar capability, although it runs about twice as fast. It has a little less SRAM, 8 kilobytes, and almost double the program storage. Now, this is a 16-bit architecture, but because of the size of the program storage, the addressing mode can be swapped into a 20-bit mode, which has some interesting implications. The largest of which is that function pointers become upcast into 32-bit numbers. Normally this isn't a problem, but when you're really tight on space, you kind of notice every byte that's missing. And it's got typical serial microchip interfaces, I2C, SPIs, and UART. So I started on this project, we had nothing. I was brought in with Tom to essentially start from zero, build a universe. So we kind of had an organic approach to a flight software architecture. We started with the bare minimum, and we actually wrote an operating system. Thread swappability. It's aware of time. It can enforce deadlines, although our mission doesn't necessarily have any real strict timing deadlines in terms of survivability. We included common memory protection techniques, triplicate voting, that sort of thing. And there's a cascaded watchdog system that allows us to enter levels of reset based on things that have gone wrong. Once we had our core operating system and we were comfortable that it was solid, we moved on to bus communication and being able to read and track hardware state. And essentially from there, we had our base level flight software. We integrated an off-the-shelf ground software package called AMPCS from JPL. I don't know what Amos stands for. Advanced Multi-Mission, I don't know if anyone else knows. Operation System, maybe? Yeah, okay, thanks. So this is an all-in-one package that allows you to command and receive telemetry from the spacecraft, and we kept it in the loop basically from the get-go in the test as you fly as you test kind of mindset. Once we had that built into the system, we established our mission-specific frameworks, our commandability, things like that, and we built the flight software based on tests. It was a test-driven approach. At the start, we were turning things on and off, and by the end, we were completing operational readiness tests with mission scenarios. So the software development process itself, we actually started off doing divide and conquer, but we were kind of hamstrung when we tried to do several painful code base merges, and we moved into a pair coding kind of approach. One computer, two keyboards, one person writing code, the other person grunting and making emphatic gestures. We actually discovered that this method allowed us to write code more than twice the speed that we could do it independently. And I think part of that is because it is a rolling peer review when it goes this way. And in our case anyway, two minds were definitely better than one. We started, as I mentioned before, from the bare metal, adding functionality only as needed. And we always expected to write our code for subsystems 3 times. The prototype, which was usually written in Python, to demonstrate what we actually wanted it to do. We took a first cut at the flight code and a final cut, and the flight code is written in C. And we're always working with real hardware. We didn't actually have a software spacecraft simulator, nor did we need one. The microcontrollers that we are using are essentially available for free from Texas Instruments. And if you do want to pay for them, they cost like $2. Our testing was essentially write something, test it, and correct anything that needed to be corrected. We did use bug reporting when things were major and we needed to do some planning about the kind of problem we were seeing. We had an approach of spend time to save time, so we wrote a lot of instrumentation code. We are able to track stack call depth, execution counts, basically the entire spacecraft state. We can do core dumps. 8K of RAM makes that easy, so we can find out the exact processor state that would cause a reset. And we definitely tried to automate things as much as possible, which included auto-coding. We wrote command tables and telemetry tables in YAML, not XML. If you haven't used YAML, I highly recommend it. It's a lot more readable. And we used Python to generate both flight and ground code autonomously during software builds. This way, we didn't make any mistakes between the two. We also put a small interactive shell in our software repository, which allowed us to do quick hardware checkouts, as in run test command, and then it prints out a test report on the spacecraft side, and it comes through a serial interface. This does not exist in the actual flight code, but it sped things up in terms of knowing whether or not the hardware we received was doing exactly what it should be doing. The picture here is us testing our attitude and control system. I actually have the software environment open, and we're doing some adjustments to the code. So what did we build? 99% from scratch. There's a little bit of initializer code that Texas Instruments uses to set up the processor. We left that in place. We built a multi-threaded RTOS we call Protos, drivers for 14 hardware devices. We have a DSN and CCSDS conformant telecom library. It supports AOS framing, telecommand framing, space packets, CFDP class 1, and AX25 frames or packets. This is for uplink, downlink, and for both uplink and downlink, a relay mode. We wrote a FAT32 file system. There are SD cards on board. We wrote a command sequence engine that allows for simultaneous sequence execution timing, mission modes, science campaign configuration. The sequence engine incorporates a language, kind of like a scripting language. It's not quite Turing complete. If we added branchable test and branch code, it probably would be, I think. There's a fault protection engine, attitude control system, and algorithms. We have the ability to patch on orbit, and a whole host of ground support tools, the debug umbilical interface, the autocoders, patch generators, the sequence generator, and some CFDP depacketization code. The code base itself is C. There are some C99 initializers. It comes in at about 15,000 lines. Half of that is drivers and file system in the telecom library. 35% is mission-specific, sequence, fault, that sort of thing. And another 15% is the core operating system. There's about 50 lines of assembly. Most of that is for stack and register manipulation. Some of it is for 20-bit address manipulation. We use the Texas Instruments CL430 compiler, optimization level 2. With small enums, we were always looking for bytes, and we got 200 bytes back simply by shrinking the size, the max or the minimum size that enumerated values could take. And of course, large code model for the 20-bit addressing mode. The finished binary weighs in at about 100 kilobytes, including reserve spaces for command sequences, core dump area, and a few other things. So the RAM utilization, we have 4 threads running. The stack is 2 kilobytes for all of them, that is combined. The call depth goes to 80% utilization, and that includes when we hit an ISR at the deepest call depth. We're running those 4 threads. One of them is an executive thread. So because we don't have much RAM, we don't have large message passing queues or anything like that, and we have an independent thread that takes care of that. And so it's a modified round-robin configuration where the executive has a 50% time slice, and the other 3 threads share the rest. Because we have essentially 3 multi-protocol interfaces, there are 4 kilobytes worth of telecom buffers sitting on board. And another kilobyte is reserved for spacecraft state, and the SD card driver takes another 512 bytes. And there's some other small variables sitting around that take up more space as well, so we're nearly 100% spoken for in the RAM department. So the critical points on this are the fact that we established a stable core initially without being able to know that our the base rules of our universe, our operating system, was easy to understand and dependable. We wouldn't have gotten very far. We established the instrumentation early on, the breadcrumbs, being able to know why and how something failed gave us a kind of an edge very quickly on tracking down bugs and finding problems with hardware as well. The automation saved us from busy work style errors. Autocoders are really awesome when used appropriately. And keeping hardware in the loop was critical. Otherwise, we wouldn't have known if our code was actually going to run and work. And of course, our tight write, test, modify loop allowed us to basically be very agile in our software development process. So after we were essentially complete, someone pointed out that Voyager had something of a similar limit to capability, perhaps maybe a little more capable in terms of software, but it's fairly equivalent. And they pointed me to this Encyclopedia of Computer Science and Technology section on the software for Voyager. The original software development for the data computer has essentially been a 2-man show since 1975, beginning when Edgar M. Blizzard joined Richard Rice to develop the flight version of the code. From start to validation to release, their tools were within sight and certainly hearing. Rice characterized the unique nature of the computer data software this way: we didn't worry about top-down or structured. We just defined functions. And that's kind of how we did it, too. I think we inadvertently, if not reinvented, we certainly revisited the wheel. That's all I got.
So who has the questions?
Are there any plans to reuse this lightweight OS that you guys built, either within JPL or, external to the CubeSat community?
It's definitely being reused right now at JPL. I'm trying to get it open sourced actually as well, so it may be available sometime soon for everyone to use.
And in terms of the project lifecycle, I may have missed it, but how long did your software development take versus, were you developing all the way up until?
We were developing all the way up until the lights turned off.
And have you guys been manifested yet? Just out of curiosity.
Nope.
Good luck. Good luck.
Good luck.
I don't understand what the 2 keyboards and 1 computer procedure is. What do the 2 people do? What's going on?
The control alternates between the people. When someone has a good idea, they are typing. When someone else needs to correct something and doesn't want to just verbally, no, do it this way, just my computer, let me show you what I'm going to do. Does that make sense?
Hi. Regarding the Blue Canyon Star Tracker, is that I didn't see much description. What did you use that for? Did you have an attitude control system?
Yeah, we are able to point. We use that to get essentially our location in space and where we're looking.
Does that give you back a quaternion that comes from it, or did you have to just?
It gives us enough information to know, yeah.
All right, thank you.
I was just going to say, we did the pair programming in the original development of RTEMS, and a lot of that code has been virtually bug-free for the entire life of the program, and it really does work. So basically, you got somebody watching everything you do and making sure that it matches what you thought you were supposed to do, that you're not doing. It's kind of the human version of what we saw yesterday with the computer static analyzing you. And I actually still love it for doing board support packages. So you get somebody who knows the structure of how to write the board support package, and somebody else who, I don't want to learn how to use your hardware. So if you get somebody who knows the hardware and somebody who knows how to do the board support package structure, you can usually whip through something because 2 people know more than one. You can pay attention to a lot more details. It's a really good technique that doesn't get used much because it doesn't look productive with 2 people sitting in front of 1 computer, but the quality goes up enormously.
Yep. Yeah, it removed a lot of our first cut typos as well, which was good.
So you mentioned you did, you wrote the flight software in C and you did a lot of test-driven development. So were you unit testing in C? So what methodology did you use really? What did you draw from? How did you do it?
We would simply write some test functions that would complement the library itself. And I mentioned that we wrote a shell. And so those test functions were callable from within the shell. And it would print out a test report essentially over a serial link.
Is the autocoding just build automation, or is it something more?
It's essentially build automation. I mean, it writes actual C code and it writes actual configuration files and script code for the ground as well. So it's kind of, it is automation essentially, yeah.
With a 2 kilobyte stack size, how are you checking the maximum call depth throughout the whole program? Are you doing that automated or just by hand?
There are, it's automated. There's a high watermark essentially that gets updated every time the thread switches, or every time a function is called, excuse me. A typical entry hook, and we simply just check where the pointer is, the top of the stack, and update if it's higher than or lower than it was before.
Can we gain access to the RTOS code? Is there some mechanism at this point?
Not currently, although I am working so that it will be accessible, open source.
I'm familiar with the Vermont Technical College CubeSat. I don't know if you followed that effort at all.
I'm not really steeped in CubeSats.
Okay. I was just curious whether most of the CubeSats use similar size processors and so on? I mean, is this a typical kind of CubeSat development?
I think so, actually. The board is used pretty widely that we used, I think, so you'll see that. Like
Is
microcontrollers.
there a community that allows you to share what you're doing, or is it fairly each one doing it independently?
It's a pretty fractured community from what I understand. Yeah.
Okay, thanks.
So I have a question about the processor. I saw that it is not rad hard, right?
Correct.
Why did you choose that?
It's cheap and low power. Right.
You mentioned that you implemented a file system. You implemented FAT on an SD card. I was just wondering if the SD card that you're using, if it supports wear leveling or if it's one of the cheaper cards.
It probably does wear leveling. We didn't want to sign an NDA to find out. So it's off the shelf. So whatever you would put in your camera or something or your phone.
Yeah, there are some off-the-shelf cards that advertise it as they're more expensive SD cards.
Okay. We might have splurged. I'm not sure.
Okay. Is that all? I guess so. Thank you very much. It was very interesting. I think we are going to take a